identify the symmetry of the graph. We have a graph that's defined by the equation 4x squared minus 5y squared equals 5. The way that we tested for symmetry is we took our equation 4x squared minus 5y squared equals 5. Regardless of what it looks like, if I want to prove that it's symmetrical to the x-axis, symmetry about the x-axis means if I have a point here, if it's symmetrical to the x-axis, it has to come down here. So for the same x value, I have a y1 and a y2, but these are just the opposite signs. So this is nothing more than the opposite of y1 if it's really symmetrical. So what I want to do to prove that it's symmetrical to the x-axis is I want to replace the y's with the negative y and see if I get the same result. So we had our test said take 4x squared minus 5, replace y with a negative y, and see if you end up with the same result. Well, of course, squaring a negative ends up making a positive for it. So 4x squared minus 5y squared equals 5 is a way that we can prove or verify that they're the same. So yes, it has x-axis symmetry. Now, if we use the same analogy, then if we want to prove it is symmetrical to the y-axis, means if I have a point on the sum that's going to be reflected across the y-axis, so let's say it's this point, if I reflect it across the y-axis, it's going to have the same y-coordinate, but it's going to have the opposite x value. So whatever x value this one is, this one's going to be the opposite. So these are opposite x values for the same y input. So I'm going to replace to prove if it's symmetrical to the y-axis symmetry. I'll replace x with a negative x and determine if I end up with an equivalent expression is what we started with. So plus 5y squared is equal 5, and we end up with 5x squared plus 5y squared equals 5. This is the same as the original, so it is symmetrical to the y-axis. And then if we continue this on, if you want to prove that it's symmetrical to the origin, then the origin has to be for every xy ordered pair that you create, the origin has the ordered pair negative x, negative y. So if this is my point here, and I reflect 180 degrees, that point would be down here, so we'd have the opposite x value and the opposite y value. So to prove that this is symmetrical to the origin, we'd replace both the x and the y, which shouldn't be any big surprise. You end up with the exact same things that we started. If it's symmetrical to the x and the y, then it's going to be symmetrical to the origin. So it has all three symmetries. What I'm showing you here is a way to do it algebraically, even if I don't know what that looks like, which is the graph of some type of circular or oval or elliptical. Actually, it's a hyperbola, but we haven't even graphed those. But I can do it without graphing, as long as I know how to do my algebraic test by replacing x with a negative x, y with a negative y, and both x and y with negatives to prove it's symmetrical to the origin. So that is letter B.